Hi everyone, my name is Romit Maulik and I will be introducing DeepHyper to you all. By no means am I leading this session. The people following me you will see will have done a lot more work than I have. But the goal of today's sort of 2-hour session is to first introduce you to hyperparameter search, which is one capability that we have here at LCF with DeepHyper, and then get you started on some test cases so that you can quickly port your applications to them as well when it comes to that. My goal here is to first give you a little bit of the mathematical intuition behind hyperparameter search and how you can use it for some of your problems. I have to warn you, I live right next to a fire station, so I don't know. You'll occasionally hear some alarm bells ringing, so just letting you know ahead in time. So I'm going to share my screen, and we can just go through the README document that's there on the GitHub page. I'm assuming you guys can see my screen now. If anybody has any trouble, please let me know. Silence will be assumed to be a yes. Okay, so this is as Taylor said, it's in the distributed hyperopt folder within the SDL workshop repo, and I'll be going through this now, but this will stay there, and there are some links over there to our full documentation, which might be a little overwhelming initially, but you can find that on our Read the Docs, where you have many more details and a lot of advanced examples as well. The GitHub repo, if you're interested in running this on your local machine, or maybe like a small cluster you might be having access to, in addition to Theta, you can visit our GitHub repository for DeepHyper. Over here, it's basically github.com/deephyper/deephyper. And the team is quite responsive, so you open an issue and you will get responses very quickly. All right, so DeepHyper, like the name suggests, is a hyperparameter search framework. It can also do something called neural architecture search. We won't be going through neural architecture search today, but I figured you should know that it exists. So there's a slight difference between the two. Hyperparameter search implies, or generally, again, these are very loose definitions, and there's a little bit of an overlap in some cases. But let's say there are some parameters in your model, your data-driven model, that generally you can tune to improve performance for your target application. That is what is called hyperparameter, and tuning these hyperparameters can be quite a bit of burden, especially if you're a grad student or a postdoc, right? You get asked to fiddle around with these parameters. If you're familiar with neural networks, then these could be the learning rate, it could be the activation functions and stuff like that. And we want to automate this so that you can have the heavy lifting be done by an intelligent framework that discovers good hyperparameter combinations for you. Neural architecture search is slightly different. Neural architecture search is something that actually searches for high-performing architectures, high-performing neural networks within a space of possible architecture. So we won't be going into much details over here, but I just wanted to let you know the difference, right? So HPS is a little more restrictive, so you've got a well-defined model in there, and you want to tune around some features of the model. Neural architecture search finds models for you, okay? Neural network models. All right, so HPS, or at least the examples that we're going to look at today, uses something called AMBS, or synchronous parallel model-based search. And this is kind of sort of the foundation of most of the HPS experiments you will be running. So I have a little bit of an introduction to AMBS. Feel free to stop me at any time if you think that there's something you haven't got perfectly. But understanding this sort of algorithm will help you devise better hyperparameter searches applications. Okay, so AMBS, so there's the M in AMBS that stands for model. It's very important that you realize that that is not the model you're optimizing. Okay, that is not the model that you're finding hyperparameters for, right? The asynchronous model-based search, the model in that phrase implies a model that is being fit for a metric that you want to optimize. Okay, so let's say that you want to build a good classifier, and you want to tune your hyperparameter so that your classifier gets more accurate, right, on some validation data set. So the model that you built in AMBS is a model for the validation accuracy, right? The output of that model will be a validation accuracy, but the input to that model will be your hyperparameter combinations, right? So a very trivial example, let's say you have a neural network and you want to optimize the learning rate and the activation functions, right? So your model in the asynchronous model-based search will take in a choice of an activation function and a choice of a learning rate, and it will build a model to the accuracy. Okay, once you have this model, you use classical Bayesian optimization arguments to actually find better places to search for your inputs. Okay, we'll go into that in a bit, right? So this is the algorithm for it, right? So the way AMBS starts is initially in DeepHyper, you'll sample some random hyperparameter configurations. It doesn't have to be purely random. If you know that a certain set of hyperparameters through some manual tuning has performed well previously, you can start with those. In the hands-on, you'll have some examples of that, right? You will evaluate those hyperparameter configurations. What do I mean by evaluate? You will train models asynchronously in parallel for all these hyperparameter configurations. Each of these models will be then validated on some held out data, right? And you will look at the accuracy on those held out data sets. And the accuracy values will be your targets for this asynchronous model. Okay, you can also call it a surrogate, for example. I'm going to call it a surrogate so I don't use model interchangeably and confuse people. Okay, so this surrogate will then be fit in step 8 over here between our inputs, which were our hyperparameters, and our outputs, which were the validation accuracies, right? Once you have this surrogate, you can then do something like acquisition function maximization, which I'm going to go into in a bit, to find the next point where you want to sample. Okay, so the first set of samples is random or manually chosen, but after that the samples are chosen adaptively in sort of like an exploitation balancing fashion. Okay, we'll get into that. Okay, so how do you set up a search space? Again, don't worry about the syntax over here. All of this code is available. There are examples that you can directly start running. But here's a like a standard type of problem over here. You have a problem class object into which you can add a hyperparameter, a dimension that you want to search over. You'll notice that these can be integers, these can be real numbers, or they can even be non-ordinal. It could be just for example strings, like in this case. And you can also add starting points, like I said. So the first hyperparameter that is evaluated in step 1 over here will be a bunch of random samples in addition to a starting point that you specified. So that is nice. Okay, and then samples from this space will be run using a run function, which basically takes these samples, initializes the model with those hyperparameters, and just fits it right over here. What we are doing is we are optimizing the hyperparameters of a random forest classifier. Could be a neural network, could be anything. It could even be a simulation. I have done that, but I wouldn't recommend it on theta. It's better to stick to machine learning. And then you get an accuracy, right? So this accuracy is returned and the model is fit, the surrogate is fit on this accuracy, okay? And so on and so forth. So over here we have an example of something you might use for a neural network. So you have the number of units, the learning rate, and the activation function, some standard hyperparameters that you want to search for. And this is how you would, for example, take a configuration, load some data, fit this model, return it, and maybe what you're returning over here is something called the R-square value. So the coefficient of determination. It's a metric for accuracy in the context of a regression. Okay. All right. So 5 minutes left. Let me speed up. All right. So let's say now that you fit this model, you've run a bunch of samples, you've got a model that gives you a mean. what you can do now is that you can construct something called an acquisition function, okay? And this is used in asynchronous Bayesian optimization. If your surrogate is able to give you a mean as well as an estimate of the variance, and there are many, many surrogate models that can do this for you. For example, a Gaussian process, a random forest regressor, right? These can give you a mean, and it can also give you a sort of an estimate of the spread at a particular point. Over here, X is a hyperparameter configuration, okay? So then you can construct this right-hand side by choosing a suitable value of lambda, okay? And over here, what this is basically saying is that if this is accuracy, if the mu over here corresponds to the mean accuracy, you want to explore locations where the accuracy is higher, correct? But on the other hand, you don't want to just go to the highest accuracy locations and not look around enough. So the variance represents areas where you have sort of a lower confidence of how nice the surrogate is, right? So you can increase the value of lambda over here to increase exploration. You can reduce the value of lambda over here to increase exploitation, right? In the context of accuracy. So if you, at the end of the day, you want to find areas where this right-hand side is maximum. So so you can see a schematic over here, right? So so let's say you evaluated two configurations, you set up this expression, and you can plot it over here for a trivial example. The maximum location of the acquisition has been found to be this place. It's easier to maximize it because it's just a linear equation. And you go ahead and sample the next configuration over there. And once you sample it, what you can do is you can refit the surrogate. Okay, you can refit it and get new estimates of mu and sigma in your entire domain. So now for a typical hyperparameter optimization problem, obviously it's not going to be a one-dimensional picture like this. It's going to be incredibly complex in a high dimensional space, but this gets the idea across to you. This is how you adaptively sample points for new configurations, right? And then at the end of the day, you collect the highest performing ones, and then you do some analysis on these, and you know, Sam and Misha and Kyle will get into that, right? So the default choice of the surrogate model in DeepHyper is the random forest regressor. So, and there's a good reason for this. The random forest regressor innately is able to handle data that's coming from multiple types. So it could be integers, real valued numbers. It could be non-ordinal, it could be strings. So the random forest is quite well suited to handle that. In addition, you can see the random forest, as the name suggests, it consists of multiple decision trees. And you know, if you're not familiar with this, don't worry about it. But basically, you have multiple predictions, right? So you can just find some mean of these predictions from one random forest, and you can also find the variance and use that in the function that I was talking about over here, right? And you can read our paper, but we compared it to a bunch of different modeling strategies, surrogate modeling strategies, not modeling, and we saw that it was superior to the others in a bunch of different applications. Okay, so so I think it's best if I leave this part now, the evaluated class object. Misha will probably be able to cover it much better, but feel free to go and take a look. I have a couple of minutes left, during which you can ask me questions, but I just want to also mention some of the cool research that we've been doing with DeepHyper recently. So apart from just purely optimizing hyperparameters, which is very valuable, of course, we've also been using neural architecture search, DeepHyper in general, to solve a lot of really cool scientific problems where we sort of outperform manually discovered architectures for a wide variety of cases: cancer research, geophysical research, and so on and so forth. So so I hope you find this framework firstly easy to use and useful for your target applications. And yeah, feel free to ask any questions or reach out to us if you're interested in some of the finer details about this. Okay, so I'll take a couple of minutes for questions about the the math behind what is happening, and then I can hand it off to Nisha, Sam, and Kyle for taking care of the hands-on. But I'll stick around for helping.
Thanks, Romit.